Hi, so I'm Alex, and this is going to be a bit different because I'm, I guess, technically an applied cryptographer, and I want to talk to you about how we use MLIR to try and build an end-to-end toolchain for fully homomorphic encryption. To give you a bit of a context of what we're trying to solve here, it's probably no secret that most of our data now lives in the cloud, and that has consequences, right? There's no lack of news articles every year about various different ways that our data rains out of that cloud. And so in recent years, we started to address this issue by going to end-to-end encrypted systems, right? Where the cloud is just passing ciphertext along, and even if there is a compromise, the adversary doesn't learn anything. And there's a very good chance that most people here in the room have an end-to-end encrypted messaging application right now. And that's been amazing. But you probably don't have any other kinds of applications on your phone that are end-to-end encrypted. And that's because messaging is relatively easy because all the server has to do is forward messages. And so all you need to do is to protect it in transit, right? That's TLS, SSL kind of stuff, or Signal in the case of end-to-end encrypted messaging. And we're really good at doing encryption, doing storage, disk encryption. But how about using data while it's encrypted? This is the realm of what's called advanced cryptography. These are techniques such as zero-knowledge proof, secure multi-party computation, or what I will focus on, homomorphic encryption. And these have only recently become practical enough to actually deploy them in practice. And so we call it homomorphic encryption because you can sort of think about it as a homomorphism between the plaintext and the ciphertext. But more practically, what it allows you to do is to compute unencrypted data, right? To ask a third party to compute a function f on your ciphertext and get a ciphertext that computes that encrypts f of x, without having that party learn the intermediates or the result. And so instead of talking to you about the math of how this works, I just want to show you an example of how we can delegate the processing of data in a really interesting way. And that's actually deployed by Microsoft in their Edge browser. And so if you save your passwords, okay, let's assume anybody uses Edge, but that hypothetical person might use the password saving feature in Edge, right? So they have a bunch of passwords that they're personal passwords. And then Microsoft, because they're not sleeping, they actively look around for leaked passwords that are available on the dark web and such things. And they have a massive database of known compromised credentials. Obviously, it would be nice if you could know if one of your passwords was in this leaked database, but for very obvious reasons, Microsoft is not going to give that to you. And for hopefully equally good reasons, you are not going to give your passwords to Microsoft, right? But what you can do is encrypt them using fully morphic encryption, and then send that to the server without using any kind of privacy. And then Microsoft can actually run a private set intersection between these two databases on the ciphertext. And the result of that is an encrypted bit that tells you whether or not that specific thing was in their database, right? And so when they send that back to you, you don't learn anything about the other people's leaked credentials. They don't learn anything about your credentials. They don't even learn which of the credentials or if any of them were in the set, but you learn that you should definitely change at least one of these passwords. And so this is the somewhat magical property of FHE, and so it might not come as a surprise that it wasn't always clear that it's even possible to do this. In fact, it wasn't until 2009 that Craig Gentry showed some breakthrough work based on lattice cryptography that showed that this is in fact practically possible. But practically here meant that a year or two later, we managed to implement it, or somebody in the community managed to implement it for 1-bit operations in 30 minutes. But that's practical in the world of cryptography. Thankfully, since then, there has been massive amounts of additional research. We've rebased it to slightly different cryptography problems. And we're now able to actually do real-world work with this, as I showed you in the case of Edge. But this is not a programming language. You can sort of compute arbitrary functions with this. But when we say that, what we really mean is, well, any of the operations in your program, they're going to get expanded into a binary circuit. And this is sort of this domain of what we call binary FHE, where the actual operations of the scheme are just XOR and AND. And then, any program that you want has to be translated into this massive explosion. And that comes with, quite obvious performance drawbacks. And so what we see actually more frequently is what I call arithmetic homomorphic encryption. And here, you're really restricted in the operations, like, no comparison, whatever. And that means if you want to do, let's say, machine learning, you get into the fun world of polynomial approximation. We don't really have this sort of holy grail that gives you both expressiveness and performance. But what we do have is upcoming work on hardware accelerators that will make this faster. But I'm not here to talk to you about FHE itself. I'm here to talk about the tooling, right? So I already mentioned that initially all we could do was individual operations. But then with these more realistic schemes, we can evaluate these circuits. But it was a very sort of low-level thing. And in fact, it's even more low-level because there's these ciphertext maintenance operations that don't change the message, but have massive impact on performance. And so what we wanted, even initially as a very basic level, is to be able to program these non-sort of an assembly style. And it took us quite a few attempts to actually get to this. And we have a paper that I'm referring to here from last year that showed just how far behind the ecosystem here was. And I don't want to diss any of these tools. They all make important contributions, but they were just too narrowly focused. And so what we're proposing is a more end-to-end toolchain, because it's not just about performing a few optimizations on a circuit. If you think about the example I showed, right, private set intersection, if you think about machine learning, think about the rich world of programming languages and tools that we have, and just how much of that information you lose if you think about everything as a circuit. So we're the first ones to introduce sort of the notion of high-level intermediate representations and optimizations on those. And then also think about the output. Existing tools think of arithmetic circuits as the output, but obviously you can't run that. And so you can run them against libraries, but as you want to sort of deploy against, I'm going to skip a bit here in terms of time, actual hardware, you're going to have to put a lot of the cryptographic and mathematical complexity that used to be inside the libraries into the compiler, right? These are lowerings that have entire PhD theses behind them, right? And so the compiler suddenly has to know how to do this. And also it has to know how to target this very odd dedicated ASIC hardware that is very much not a CPU. And so with HECO, we leverage the strength of MLIR, right? And I don't think I have to sell you on the idea of how great it is to be able to reuse existing dialects. And we sort of show how you can construct this. Currently, our main implementation goes out via emidc to existing libraries. But the long-term goal here is to eventually be able to go to hardware, either through LLVM or directly to ISA. And there's been some concurrent work that was actually presented at Euro LLVM. Oh, sorry, they're cutting off the bottom bit. But if you look for prototyping a compiler for homomorphic encryption and MLIR at the Euro LLVM dev meeting, those group from South Korea actually did parts of this, but not the really tricky part of going from the abstract notion to the actual math. And with my last 2 minutes, I think, roughly, I want to quickly give you an idea of what we're really interested in doing. Because, I mentioned already code generation. These accelerators that I've been lucky enough to sort of be an Internet Intel to help develop, they look really funky. And I think we're really beyond what LLVM and MLIR by default can do. Also, abstractions. The community is great at standardizing crypto, and there's an ISO standard for FHE being built. But the very, very early drafts of sort of API standards died because they were too early. And now that we have lots of people in this field again, we want to make sure that we don't run into any of the pitfalls that this community has learned to avoid. And so I would be very interested in hearing about people that are interested in joining our informal roundtable, where we have a lot of the FHE stakeholders, but maybe not enough of the MLIR LLVM stakeholders. Yeah, I'm going to skip this and just say, check out, if you want to know what an FHE optimization looks like and why they're measured in orders of magnitude and not percentage, check out our paper on HECO, our homomorphic encryption compiler. Thank you.